on designing this platform and really have fun with this. We have data that will be distributing on our from our server, so I hope you can ping it. All right, I'll let you go ahead, you.
So can you see the slides at this moment?
We can see your slides.
Okay, sounds good. So yeah, I'm here to give a short introduction about our work on doing cross correlation using DAS data, and also move this workflow on the cloud. So it's like combining ambient noise cross correlation, distributed processing, and cloud computing all together. And it's a work with Marine and also Chenxing, who developed the noise pi, and we are like modifying that packages from broadband sensor to be adapted with the DAS data. Sorry, can you see my screen at this moment? It's all black on my screen.
It's black for us too.
Okay, so this is probably good. So I'm just giving a short introduction to myself. So I get my bachelor degree in geophysics in 2020, and I'm currently a second-year PhD student at University of Washington, and I'm also a duty seismologist at Pacific Northwest Seismic Network, who sporadically do some face picking works, like catalog building. And I started my coding probably with some of the QBasic. It's like I haven't never used it after learned it, but it's like the coding 101 for me. And I coded in C MATLAB for training in undergraduate, and started getting to the Python and Julia during my PhD study. My interest in most involves high performance seismology, machine learning, distributed acoustic sensing, and these keywords you've heard during this workshop. And here is a snapshot of me developing Zealand nodal in Tillamook State Forest last year. Speaking of this node, it's kind of interesting because we have used these sensors, the sensor arrays, to have a dense observation, and in order to increase our spatial resolution, how seismology can see under the surface. For example, we're using this 6 month long experiment in Long Beach area with 5,000 nodal seismic sensors. Average spacing between the sensors about 100 meters. So another example here is this LASSO experiment in 2019 with more than 1,800 sensors and 400 meter spacing on average. So this we call seismic dense array are usually formed by thousands of stations, and the average spacing could be several hundred meters. I'm not sure what's happening here. Depending on the area of study, but this battery in these sensors are usually supports months of recording, but it still requires tremendous field work from PhD students to support, and PIs. You work together, deploy them, and finally retrieve them back. And later we know the story. We have the new technology called DAS, distributed acoustic sensing. So using a unit called DAS interrogator, DAS uses repeated laser pulse along the optic fibers up to 100 kilometers to measure phase change backscatter light, which occurs due to the strain rate of the fiber. And figure here, I'm showing the records of an earthquake from a single seismic station, and it could be a 1D array with only one time axis. But for DAS, it basically has 2 dimensions, still one time axis, but also a channel axis. You'll see this FOSA experiment near Sacramento as an example turns this 23 kilometers cable into 11,000 channels with 2 meter spacing. Very dense, right? You could see this arrival from earthquake through the entire cable, and there are also some strip-like signals, which probably corresponds to the cable segments aligned with Interstate 5. and it turns out to be the cars driving along the cable. So using this technology, it is possible to have a dense seismic observation system. So it's similar to dense array in terms of the number of channels, the length duration of the recording, but this channel spacing could be meters, and it requires much less field work to conduct a DAS experiment. So what we can do with this DAS data, there's a lot. Like we can do fault zone detection, like from this Lindsay et al. 2019. We can do surface imaging paper last year using the ambient noise cross correlation to have a high resolution subsurface structure. And we can use DAS underwater cable to detect like wildlife, like whale calls. There's also some applications in mirroring the traffics using the urban cable. So, however, there's definitely some challenges and bottlenecks in ambient noise seismology to fully utilize this data. So, first, DAS data is basically very big data. It requires better cyber infrastructure and probably better data formats to share and archive this data. And DAS is also large, what we call large in the number of sensors or channel. We would need to combine powerful tools with advanced computing infrastructure to support the computing involved here. So we are trying to provide solutions that accelerate ambient noise seismology research using that involves this DAS data. So let's first take a look at some of the most recent DAS experiments. So each row here represents a single DAS experiment. We could see different configurations here in terms of the recording duration, channel spacing, sampling rate. But if we focus on the size of the data generated by DAS, this experiment generates tens to up to 1,600 gigs of data per day. This is a huge amount of data that could easily reach terabytes or even petabytes for a research group. So, IRIS is like the national data center for seismology. Like we request data very frequently from IRIS, just like Marine just do on the cloud. It's a huge data center. However, the amount of DAS data generated by the experiment only listed here in 6 or 7 years has already reached the total amount of the data archived by IRIS since 1992. IRIS is not providing any DAS data service at this moment, but the huge data volume is one reason, but how DAS data are saved also makes it hard for data archiving and sharing. So how are DAS data saved? Some recent DAS interrogators save this data in hierarchical data format F5 or HDF5 format. It supports hierarchical structure, and here's a breakdown of the structure of the example H5 data. Here NT shows the time sample and the N channel indicates the number of channel. Usually, this raw data set would take more than 98% space of the entire file. It's a 2D array of shape, number of channel, number of time sample. There are also sometimes attributes attached to this data set, which contains important metadata during the for the experiment. They are very small key value pairs and don't change much frequently during experiment. They could change actually. The problem with these attributes is that we don't have a good convention for them regarding what metadata to keep. Research Coordinate Network or DAS RCN looks promising at this moment, and we'll see later how we store this metadata in our solution. So what I'm showing in the previous slide is just 1 minute of recording. So every minute, DAS interrogator will output one file. So these are separate files, but if you append them along the time axis, it will form a continuous recording. So 1 minute of DAS data corresponds to a 2D array with length fx times 60 seconds. Fs is the sampling rate. If you get the data into 1 day, then just times get this number of size of data. 1 month, approximately 2 terabytes for this specific experiment. It's effectively a very wide matrix with fixed height. So then comes this problem is that, what if we want to analyze some signal longer than 1 minute? For example, the recording of an earthquake could easily extend across many minutes. The common solution here is just to open each 1 minute file, extract the data, and move on to the next. So 1 minute recording are just concatenated to get a longer one for processing. Let's go further than that. What if I only want small segments of the data? For example, some of the cable segments are above the ground and may not have the good quality. It is possible to choose a 100 a subarray by just getting the data rows I want. But however, these operations are almost based on the assumption that the data is saved locally. So if a researcher does not have the raw data, it is usually required to make a full copy of the data from the remote server. It is not good. Remember the typical size of the DAS data listed. You may not have an interrogator or cables to run this experiment, but for sure you will need to have storage to save the data locally. But why is that? The answer is actually inside of the H5 structure. We say H5 is self-describing hierarchical structure. It supports compression. It supports user-defined attributes. And theoretically, there's no limit how big a single file is. But all of these structure attributes, metadata, need to be mapped into a linear disk space, meaning that this data is unevenly distributed in the file. So H5 uses a pretty complex mechanism to track where this data are located in the files. The libraries will usually need to read these headers or data blocks to first decode the structure and address the actual data in the file. This process requires several reading operations. It will get more complex if data are compressed. So the easiest way to access remote H5 data will simply make a copy locally, even if the data is saved on the cloud storage. So to help solve this problem, this is what we are proposed to solve this big data problem. So idea is we convert H5 data into some cloud optimized data formats, more specifically TiDB or ZAR. We deploy Minio as our local object storage, mimicking the cloud object storage. So combining these two, we create a platform called DASstore that is able to provide data service in a much more efficient way. So first, we convert H5 into formats that are designed for cloud. One candidate is ZAR, which chunks subarray as individual objects in an object storage. We designed the chunking schema in a way that for common long time series request, only a small proportion of the entire data set is requested, highlighted here. This avoids accessing other unnecessary data. So a similar data format is TiDB, which use database to index the array. Both formats supports compression, saving key value attributes, have self-describing hierarchical structure, just like H5. But most importantly, they allow subarray request. You don't need to make a full copy of the data, just request and get the data you want. The way we chunk data is critically important for these two cloud optimized formats. For example, if we chunk the DAS data along the time axis and try to get time axis from 100 channels, we need to access all chunks with very low data efficiency. The data along the time axis are also usually numerically close to each other, which affects the performance of the compressor we choose. I'm skipping some of the boring benchmark sections that help us decide the best chunking schema, but the strategy for ZAR can be summarized as follows. Writing a big chunk is fast, but since they are much bigger, there could be more network overhead, especially if someone is not requesting that much data. Having a smaller data chunk gives you better reading performance, but it's slow to perform the data conversion. And if you have too many small objects on the cloud or your local storage, it will still slow down the server. So one should optimize these parameters based on the data sets, as well as how data are most possibly read. So another idea of our platform is to use object storage. We're not in the cloud, but we can still deploy one local object storage using this menu. For example, here I uploaded 1.6 terabytes of DAS data, which gives more than 1.8 million objects. There are advantages using this menu as local object storage. First, it's open source. You can easily deploy this through Docker. As an object storage, it has good scalability. More importantly, it provides access control through the credential keys and secret granted to users who has the proper permissions. It also uses the same API as AWS S3. The researchers could upload the data to S3, and their code would need very little modifications to work on AWS. So what this storage server could be? First, you could basically use it as a PI level data server that shares the data within the group. For example, some grad students want to use this data, just access that server, or the research group in the other department, as long as you have the connection through the campus network. We can also publicize our data storage outside of the campus, like people in the other institutions can access data through the network. Yeah, and as you develop your code on your local machine using this data, you could easily upload your data to the commercial object storage like Amazon S3. Again, our local server is S3 compatible, so you won't need to modify most of your codes, as we will show later in the tutorial section. And we push the data to the cloud, and we can use the powerful resources available on the cloud. For example, running all 500 virtual machines to do cross-correlation at the same time. That's something we couldn't easily do on our local storage. There's another potential advantage of using this framework. Cloud storage can natively serve as a data center. As we upload data to the cloud, we can grant permissions to those who want to use the data, or simply publicize it, just like SEDC data product on the AWS S3. So yeah, to summarize, this work we are proposing to solve this big data problem. The DASstore client with the DASWay server, which is currently deploying in the UW department. Speaking about this another problem about this large N problem. We need to develop these efficient tools, but I think Maureen has given a pretty good introduction and tutorial about the NoisePy, and that's the tool we're going to use. For the traditional broadband NoisePy version, we just cross-correlate among the stations, right? The NoisePy for DAS follows almost the same logistics and framework. The difference here is that we correlate channel pairs. For the dense array experiment that spends a lot on several hundreds of thousands stations, DAS can easily reach several thousand, even 10,000, get million or billion cross-correlation operations in a relatively short time period. So in the following section, I will explain how NoisePy packages works on this new DAS dataset called CDAS. So the CDAS dataset is I'll just give a short introduction before we get into how NoisePy for DAS works. The CDAS dataset uses a dark fiber connecting UW Seattle and Boston campus. So the cable basically goes from directly to our lab and it plugged into a DAS interrogator. And the experiment lasted for 11 months, I believe, beginning in April 2020. About 2,100 channels are evenly distributed along 10-kilometer segments, highlighted here. And the channel spacing is about 5 meters, sampling at 100 hertz. So this basically generates 72 gigabytes of data per day. And the raw data is saved as a minute-long HDF5 files, as we showed previously. Remember that this is 289 channels DAS data. So using NoisePy, we would use the first source as the virtual source and cross-correlate with the rest of the channels. You can cross-correlate with itself, and so it basically includes autocorrelation. Then we move this virtual source, for example, this channel 200, just basically cross-correlate with the rest of nearly 1,900 channel pair, continue moving, and we're basically moving this virtual source. And we don't need to recompute this cross correlation with the channel before this virtual source, since this should be symmetric. And for all 2,089 channels, we reach 2 million cross correlation in a single time chunk. But it's good that this computing are independent to each other, so we can parallelize it, and we will show that later how it works in the tutorials. And we're also having this passing client from the DASstore to request the data from our object storage server running at this address. DASway.ess is a department machine. And we can do a subarray request from the channel 500 to 1100 from the start time and end time, basically a half an hour data set. And here's how it looks like, the raw data. You could see the coherent non-seismic noise like the strips. There are cars moving. There's seems like a data gap for some unknown reasons. I remember that this is just a subarray request. You don't need to request the full 2,089 channels. And we go further than that. We want to do a ambient noise cross correlation using this both platform. So we develop a DAS cross correlation workflow. First develop this workflow locally, but it's a very compute intensive and will cost too long to finish on local. So we upload this 1 month of DAS data to the AWS S3 bucket as a showcase. And this is where we can upload the data from local to the cloud. So basically the rest of this block are performed on the cloud. The code we are using on the cloud is almost the same we use locally, given this S3 compatibility of the platform. And the cross correlation of 1 month DAS data is split into 100 smaller jobs and distributed over an auto-scaling group. The group basically automatically manages the type and the number of EC2 instances based on the job requirement. So each smaller job will request 3 to 4 hours of the DAS data from the S3 bucket, performs correlation, and writes an hourly stacked cross correlation function directly to another S3 bucket. So previously, remember that previously we're using SDF as our intermediate data product, write local onto the local drive, send and upload it to S3. But here we'll get rid of that, and instead we're using a TidyDB, which supports write directly from the instance RAM into S3 bucket. So there's almost no local storage required except those necessary for the system and the code. There is also a short cost analysis of this cloud workflow. It's pretty attractive to me. Hosting the data on the cloud mostly costs $1.3 per day. It's 1.7 terabytes. The compute cost is cost most, I think. And we're launching almost 500 vCPUs, finish the computing in 12 hours. And yeah, basically, I remember correctly, it costs less than $100. And for storing this hourly stacking cross correlation function, it basically costs $1.8 per day. But you can choose to download these cross correlation functions to local, which egress cost may apply. But you can also perform all the analysis on the cloud using an EC2 instance, and you don't need to pay anything for this bytes between EC2 instance and the S3 bucket. Yeah, this is what we got from this data experiment cross correlation, and here I'm using this source 500 as a virtual source, and you could see this a clear move out probably from the surface wave, and you can further measure the phase velocity, group velocity, and doing a tomography through the dispersion, extracting this dispersion. And basically this simple plot involves 100 billion cross correlations total. And there's another GIF version as we move this virtual source from 500 to almost 1100 index. Yeah, looks pretty cool. And yeah, this last slides of this tutorial, this lecture part. Thank you for your time, and you could get more information about these two projects through this QR code, or the links is simply here. For the rest of this section, I will just go to the tutorial part, and we can try to query the CDAS data and do a quick noise pi cross correlation, either on the cloud, Google Colab, or if you have Docker installed locally, you can also do that.
Thank you so much. That was great.
Thanks, Marie. I'll just so basically on the Google, if you go to the Google slides I'm sharing here, it basically provides three options that you can play with this data platform. First, on Google Colab, if you go to this colab.research.google address, I'll just send this link here. So if you go to this Google Colab, in the GitHub section, you can copy paste the GitHub URL, and it will show up these notebooks. And you can simply run these notebooks by running each of these blocks. Remember that depending on your running environment, you may need to run either of these blocks. If you're running on Google Colab, you can skip this one, right? You don't need to. You have to install all of the packages through pip install. Have the source code. Apologies that I haven't made it through the pip install. Yeah, hopefully soon in the future. But for those who have the Docker running on the AWS EC2 instance, I'll lead this part, maybe launch my own instance and try to run it synchronously with participants. And if you have your Docker installed on local, you can also simply skip this EC2 instance and put our image and play with these notebooks. But I would mostly focus on this Docker on the AWS EC2. So what I'm doing here is to go to our console, log in with my IAM user and username. That's what we have been doing. Here I'll have to ask you to switch to the region of US West 2, because that's where we put our DAS data. Haven't made a copy in other region. It's relative because it's still a big data set. So if you launch into this console, you can switch the region into US West 2 on the top right section. And I will basically running everything from the startup, from scratch. Yeah, just to illustrate. But there's also tips to run the instance from the tutorial yesterday. If you need help, you can also reach out there. So I'm going to launch my instance. Name maybe EU test DAS. I'm using an Amazon Linux server. Probably T2 Nano. A micro will be too small. I'll just try T2 medium with 2 virtual CPU and 4 gigs of memory. I just create a key value somewhere, I think. Oh, here it is. You can use your own one. And in this section, using the existing security group, I'll just choose this default one because we have already preset the policies that allow connection through the port 8888. So by default, this is not allowed. You have to manually go through this part. In the advanced section, yeah, I don't need to go into that part. I'll just pause here a little bit and see if people are getting this. Okay, so now I'm going to connect to my instance. Should be this one. Yeah, there's a tip to connect to your instance is that if you click your instance, there's a connect button here. If you want to use your SSH client, there's a quick command you can copy paste, and later I just open my terminals. Here's where I saved my PEM key file. Connecting to the instance here. Yep, here's where I am. And I will follow the tutorials from yesterday to install the necessary packages. There's a code block here. I would just copy paste all of them into my Docker not Docker, my apologies, EC2 instance. It will install the Git, the Docker, Miniconda, mostly for the Python environment. Yeah, I'm also trying to do that at the same time as the EC2 instance is running. Yeah, also note that if you are running on Google Colab, you will need to restart this runtime here. There's a restart runtime. Basically, the first time you install these packages, this is required basically for the OpsPy to run properly. It's kind of annoying, but yeah, has to be done. Okay, here. I'm just paused here a little bit and to follow up on the collab section. Okay, so it's basically if you say climbing and down, you are ready with these 2 lines of code. And remember, you have to restart the runtime. After that, you don't need to reinstall everything because the runtime is already here. And you just run this, append the source code. And you don't need to go into this cell that designed for Docker and running locally. So you can just skip into this import necessary packages step 0. Okay. Yeah, I'll pause it there a little bit and get into the Docker instance if someone is running that. And after running this required software on the EC2 instance, we will need to start the Docker server. It's not showing anything, but yeah, the Docker service just started, and we will pull the Docker images from this GitHub repository. It might take some time. Okay, basically it shows now that we have already have the image locally on our EC2 instance, and now I'm going to run this Jupyter notebook in this instance so that we can interact with the instance. Oh, sorry, there's a missing space here. Okay, so similar to yesterday, I'm just copy and paste, getting this token ready. I'm going to pull where is it? My public abstract address. Copy it here. I'm using 8888 as a port. Now I see the Jupyter login page. Copy this token here. Yeah, when you get into this Jupyter environment, you would be able to see this DASstore Docker file, and most importantly, this notebooks. There's an example noisepy for DAS, CDAS. Click it, and after that, you will see exactly the same notebooks as this collab. But the difference is that on this Docker environment, we have already have everything stored together with the Docker image. So we don't need to install anything. So simply run this, get into the source code, and you can now run this import section. Yeah, for the users running on the AWS cloud, I'm suggesting you running this block because remember that our DASstore platform is compatible, S3 compatible, meaning that it can either request data from the Amazon AWS or it can also request data from our DASway storage. So for I think definitely AWS cloud is faster if you are running your instance on the EC2 instance. Here, for example, I'm running this EC2 instance. I'm just skipping this part and using the S3 as our endpoint to request the data. For those who are running on Colab, you can also try to request data from our server. These are actually two different places. Let me remind you again. So this one is a server running in the ESS department, and you will request the data from the Colab, basically Google server. And on the EC2 instance, you can request this data directly from the S3 bucket. So like different solution for different running environment, but the code are basically the same. Yeah. So I will just finish the rest of the notebooks here using the EC2 instance. So you see there's a bucket. Basically, this is similar to the folder name as a file storage, but it's different. Different buckets are isolated with each other. So for SCDC data, it has SCDC PDS, if I remember correctly. Here I'm using the CDAS-December 2022. And there's a secure means that we're using HTTPS. And anonymous request is set to true. This is a special policy applied to our data. So in order to allow public access during this workshop. Okay, so if you run this block, you will see something like this. It will show the endpoint, the path, if you are reading in anonymous mode, and the backend, which is SAR. Yeah, we store some of the metadata in this client together with the data. Basically, for example, here it shows the acquisition starts at 2022 December 1st to the end of the year. This is not actually how CDAS experiment lasted, but we only uploaded 1 month of the CDAS data for this ambient noise cross correlation computing. And there's a get metadata function that you can have all the metadata available. Here we are following the DAS research coordinate network metadata convention. All of these metadata are saved as a key value pair. We're not fitting all of them, but those necessary for the further plotting and analysis. For example, here the channel spacing, the acquisition sampling rate, start and end time, total number of channels, and gauge length. And yeah, you can basically request it here. It's a key value pair, and in Python basically it's a directory, and you can visit it through the key value here. Yeah, next we are getting to this client.getData function. That data is by nature is a 2D array with the time dimension and the channel dimension. So when we are requesting this data, you will need to specify like the channel range and the time range, right? To get a submatrix from this 2D giant matrix. So there are 3 parameters that are required to use this getData function. So the first is this channels. You can provide the channel requested as a NumPy array or list. Here, for example, I'm using a NumPy A range to specify the channel from 500 to 1000, basically 500 channel. There's also a start time and end time in UDC format. You can enter it as a Python string. For example, here it shows 1 minute of data starting from 1 p.m. 1:30 to 131 on the day December 15th. So it will return you a data of shape 500, 6,000. So we have a short explanation of this shape. So 500 is the number of channels we have, and 6,000 is basically 1 minute of data times 100 sampling rate, basically 60 times 100. And this is basically the time spent to download this subarray data. And we also noticed that we're not having a full copy, having any copy of data on local. So data is loaded directly into the RAM. So you don't need to have like gigabyte storage pre-allocated to store the data. See, this is the part we're interested in. Yeah, so the next part I'll introduce the coarse correlate with noise pi for that. Oh, before that, I was running that asynchronously. On the Colab, I use the DASstore. It's showing basically the same thing, but different in the endpoint, which points to our machine. I'll skip this part. It's showing the same metadata. Probably take longer time to request data because we don't actually have the powerful infrastructure than the AWS, which probably makes sense.
Hopefully it won't crash.
Yeah, this is the first time we are having more than 10 people or 20 people, I think, requesting the data from all over the world, which is really a good test to see how this platform works. Okay, well, it works on my end. I'm just monitoring a little bit here. Anywhere if we're seeing anything. Yeah, thank you, Maureen, Chibin, and Lindsay, helping debugging this part.
I mean, maybe we can hear a few from others if things are running. I personally ran into a bug, so I stopped and I started helping others.
Right.
Is
So
anybody? It's okay. I'll figure it out later. Is there anybody who's? Are you cross-collating? Who's cross-collating? Who downloaded data? Thumbs up. Are you still here? Thumbs up. Thanks, Yuan. 2. Yes. Awesome.
Can I see that?
4. That's great. I'm pretty sure many of you have. It's the first time you're actually cross-coding DAS data. Because this is heavy computing, huh? Although made easy.
I cannot see. Oh, here it is.
There's no bad question also if you want to ask.
Oh, yeah. So Felix, you're interesting how you can pull the URL. So if you go to the AWS instance panel, for example, yeah, I believe this is your instance. If you click it, and it will show up here. Basically, you copy paste it.
Yes,
or you can connect, and in the SSH client section, you can copy this SSH connection command using this copy icon, I think.
Could you drop that SSH into Slack?
Yep. But remember that people are using different key file and having different IP address. So this command definitely differ from one to another.
Yeah, I'll change the key file. I just didn't want to type all that over again.
Okay. I think at the same time, I just play with the codes here. 800 channel, maybe I'm just requesting 1000. Same time.
Yeah, and as you play with the channel, there was some discussion about the type of fiber and what it's doing. And so this is one that goes from UW Seattle to UW Bottle. And you can see that very high red and large blue values on this plot right now. I think these are channels that are above ground in the power lines or telephone lines. And so they don't record anything. We just, we're lucky enough that the university granted us access to that fiber. Some institutions charge depending on how busy a fiber can be as a rent fee, but this one is not over deployed fiber, so that's why. But yeah, there's parts of it that are above ground. For those who are trying to run Jupyter Hub, please go back to the tutorials that are on the Jupyter book to see how you connect. So basically, when you are on AWS, I see more questions about it. You cannot just run Jupyter Notebook. It will show up on the screen that's on a different computer, but there's no physical screen. And so you have to type the command -IP000 and then use the public IP address of the instance to then connect your browser to it with the port 888, and then copy the token that was on your terminal into that browser as a login. And that should be able to open it. And, any suggestions on how to improve these tutorials is super welcome. I know we didn't do well at Windows, and we'll be taking screenshots to get you more. So I guess it's worth still talking about this because there's still message coming up. Please listen. When you open the Jupyter Notebook in the terminal on the cloud, it would launch it on the cloud. There's no display. There's no browser that's connected to that computers. So go back to the tutorials we had yesterday, where we discussed about what to type. So this is an example that you was showing. When you type a Jupyter Notebook -IP0000, it will launch a notebook, but to connect to it, you have to use the public IP address, which you can find on the console, on the instance. Thank you very much. Voila, you can see on the right, public IPv4 DNS. So use that to put it on the browser, and then use the 888 port, and that should show up as your notebook platform. You need a token, And the token is what is on the terminal.
So,
Complicated.
Felix, I'm seeing you're having a different security group previously. I just send you back to the default. Would you mind try again this notebooks? So Julian, you have a question about on the AWS notebook, when the data is loaded into RAM, what's the maximum data volume I can load it simultaneously without the notebook crashing? That's a really good question, and I'll test it at this moment. Okay, actually, I'm having as I remember correctly, I'm launching a T2 medium-sized instance. So probably it has 2 gigs of memory, I think. Not here. Used to what edge top. Sorry for that. Yeah, I have basically more than 2 gigs memory available. So I'm going to request 1 hours of data. I think it should be good. Basically, you can monitoring your RAM consumption as a backend. Here the RAM is mostly the limits and the bottleneck. But if you want to load more data at the same time, you can simply launch a bigger instance with more memory available. So we need to carefully design this workflow, like the type of instance to use that best suits your noise cross-correlation workflow. Yeah, you see here we have already load 1 hour's 500 channel data, and basically it costs 1 gigs of memory, I believe. We can definitely try to get larger, for example, 1,000 channel. Actually, AWS Rebucket is pretty powerful as supporting these resources and requests, especially you are running on the cloud. So it's like we're launching 1 hour of data for 1,000 channel, getting close to the cap actually. Yeah, hopefully that answers your question.
If I may bring a little comment on use NoSPI workflow here, compared to what I showed earlier, where we kind of stream or download the data locally, and then we dump the data into an ASDF locally, and then we upload. And I was telling you, even locally, like writing X5 is slow. Part of the innovation that I think you put there is the idea of using S3 as the intermediate storage system, because it's so efficient to write to an S3 object using this StarDB platform. And so it's considering S3 as a temporary storage is new, I think. Because we always think of like my local node, my local storage, I work on whatever infrastructure I have here. But if you consider that S3 could be your temporary infinite size storage and use this cloud optimized format, it's actually very efficient. So I would say like use performance on compute time for using NoSPI is a great part due to that engineering of using S3 as the intermediate file storage. Now S3 is expensive, so you just really want to do this temporarily, because it costs like hundreds of dollars to store a terabyte per week or something. No, sorry, 100 terabytes. And I was looking for the SCSN. So anyway, it's expensive, but using that as the intermediate storage is practical.
Okay, I'm probably give the rest of time running this noise pipe for DAS. Most of these parameters and framework are similar to the noise pipe broadband version. Define the sampling rate, frequency of interest, perform some frequency and temporal normalization using cross-correlation method, and we use a 1 minute cross-correlation length with no overlapping. Basically using 60 seconds, and we only perform this cross-correlation using this 500 subrate channel. So remember this plot that I'm not quite personally interested in. For example, if you are not interested in using this noisy part for computing, and you can just simply choose this 500 subarray for computing. Let's see. On this block, still using this kind to get the 1 minute data. So this is how it looks like, and perform some of the pre-processing and run the FFT and select the channel pair based on the to noise ratio, the data quality. We will skip some of these channel pairs that does not have a reasonable standard deviation. And then we'll station is not cool. Did I skip something? Okay, here it is. So with the first channel, we cross correlate with the rest of the receiver, moving the source. As you see, the cross correlation number of correlation gets smaller, and computing just gets much faster and faster. And let's also do a 10 minutes linear stacking. Probably we'll finish in 1 minute, hopefully. Oh, I think I'm getting the end of this session, but I'll finish this part. Just running the cross correlation part. So in this cell block, we are sequentially get 10 minutes of data doing cross correlation on each of these 1 minute data chunk and linear stack them. At the same time, I'm also measuring the time we spend on data querying, highlight here, and the time we spend on the computing. Using this two variable T compute and T query, and we will plot it and see how long we spend on data query and how long we spend on the computing. Okay. Takes longer. Probably it's because it's a pretty old and small instance. It should be pretty busy. Honestly, it's using just one CPU.
Yeah, this is where you should wait. But if you don't want to wait, we can should consider moving this correlate function on GPU, maybe.
Yeah, definitely an important enhancement to this function.
If time is a constraint, yeah.
Yeah.
But we could also be patient. Our research, like how long does it take to write a paper? In trying to make things always faster and faster, it's really like, well, you're gonna take 3 months to write a paper, so
yeah,
it's okay to wait.
Well,
Except that
still a lot actually. It's 125,000 cross correlation operation actually. So also running this at the same time with on the Colab, querying the data from our our local storage.
It's probably the most queries for the single data sets that we'll have, because others will query other types of data.
It's getting close.
Oh, let's bid. Go for it.
You see, we spent three seconds in data query from S3 and the rest 186 seconds in computing. Well, basically that we want to skip this part that we spend much time making data copy from remote to local, especially you are getting into terabytes data set. Yeah, you can visualize it probably in the move out and cross correlation function. You can save this as a ASDF, as previously used in NoisePy, but I will just skip that part and stop it. And we are just give a short introduction. We're using TiDB as the intermediate data to save this data product. For example, we write the entire cross correlation function on the local, but it is also possible you write it directly to S3 so that you just skip the local disk. And actually, it saves a lot of money actually to on the cloud to run this workflow if you just skip the local storage option like EBS, because sometimes it can be pretty expensive. I'm kind of forgot to clear the memory when I was doing the memory out of memory test previously, but yeah, it's okay. It also answers the question when we are having this notebook crash problem and out of memory is basically when I've resolved data 1000 channel for this small tiny instance. Let's see how it looks like on the other side of the collab. Yeah, I'll just leave it open, but you can feel free to run these tutorials locally, Colab or AWS anytime you want. Yeah, we will leave this CDAS data open during this workshop. So,
but please, if you use the S3 bucket, use it on EC2, if possible. Just please do that.
Yeah,
because we don't want to pay for egress.
that's a lot actually.
Yeah, so you either on Colab or on your local and you query from DASstore, or you can be on EC2 and query S3. That's the best way. Okay, it happens that Yiyu is giving another tutorial this afternoon. And so in the, looking at you, don't be too tired. I want to make sure you save some energy for this afternoon about this ensemble learning. So at this point, I'm going to zoom off and take a plane. And you should feel free to stay, but you also feel free to save your energy for this afternoon. And I think we'll reconvene at 3. Was that the time for the afternoon session? Was it 2 to 5? 2 p.m. in 2 hours. A good break to get outside. And yes, Alex, 2 to 4.
Yep.
Cool.
Okay.
And so that's going to be a really exciting session. You can keep your instance going and keep practicing and be on Slack. Answer. We'll be live asynchronous on Slack.
Yep. And feel free to reach out to me if you have any questions and on this project.